Hello, welcome back to Math 332. This is linear algebra, and this video we are going to look at some of the concepts, especially on the concept of span, independence, bases, dimensions, and coordinates before leading to the concept of change of coordinate with respects to different bases by utilizing a matrix that we call transitions matrix. So some of the material here will be review material of the important concept that we learned before spring break. And because this is just a review, so we're going to go quickly on this and we're not looking at all this example in detail. And we will be following the notes that you will find on Blackboard. And these are also the notes that I printed out for you before spring break. So let's get started by looking at the concept of span. So this is one of the major concept in linear algebra that by now you should know it very, very well. So let me say that again. So given that you have these two vectors in R2, and the span of these two vectors, which we call vectors u and v, is written as a linear combinations of these two vectors. It's a collections of all the linear combination of these two vectors. So written it out, the span of u and v is given by this. So always remember your k1, k2 is always real numbers. And changing, and the things that's not changing is actually these two vectors u and v. Okay, so we have answers questions like this before, whether or not this vectors is in the span, whether or not this vector is in the element of the span, so on and so forth. So these are very basic concepts that you should know by now. And the slightly more abstract concept is the questions involving whether or not, say for example, in this case, the same vectors 1 and 2 and 3 and 4 is the entire span, which means that whether or not this set is R2, which means that can every elements in R2 can be written as a linear combination of these two vectors. So we have seen this before. The main things to compute is to pick an arbitrary element, let's say B1 and B2. This is an arbitrary element in R2, and try to figure out whether or not for this fixed but arbitrary elements, can you always find a K1 and K2 such that K1 of this and K2 of this will equals to this. If you can always find a K1 and K2 for any arbitrary B1 and B2 right here, which is an element in R2, then we will say that that two vectors span the entire R2. So this is all the same regardless of what kind of vector space are you working on. So here in the notes, you will see that, say for example, in R3, this two vectors is not enough to span R3, which means that in this case, you can find some vectors that cannot be written as a linear combination of these two vectors. And we can actually change space and looking at, say, for example, vector space involving matrices of size 2 by 2, and we can ask the same questions. We can say, hey, given this A1, this matrix, and these matrices, what is the span? So again, the span is defined the same as before. So again, here, this A1, this A2, this A3 is fixed. They are not changing, okay? The things that are changing are this variable K1, K2, and K3. These are numbers. So if the question ever asks you like, hey, is this vector can be written as a linear combination of these three vectors, then what they are asking you is asking you to set up these equations and see whether or not you can find K1, K2, and K3 such that you have this equation, this equality hold. So from here, you'll be able to extract 4 equations, and now we are solving system of linear equations. So all these problems always end up solving a system of linear equations. It's just that what kind of linear equations you need to solve and how do you set it up, that will involve the understanding of the concept. So the concept of span is pretty straightforward, and these are all the examples that you have seen before actually, and we can also always switch the vector space from R2 to R3 to Rn to spaces of matrices, spaces of polynomial. None of the definition change. It's always the same because we already studied from before that all the concept that we developed work for all vector spaces. So so if you are in Rn, if you are in spaces like this, matrices of size m by n, polynomial of degree at most n, function spaces, this is all this concept work. Everything works. So make sure you know the conceptually how this definition definition extends to all these vector spaces. So again, same thing if you're in P2, you can see that if you're asking what is the span of all these vectors, again, these are linear combination of these vectors. Do you see that I say these vectors? These are vectors, okay? So you might say these are actually polynomial, they are not vectors, but remember, every element in the vector space are considered as vectors. So with this perspective, we are actually doing everything just like Rn. So these are same setup. If they're looking for the span of these three vectors, this is a set of all the linear combination of these three vectors. And again, if they ask, hey, this polynomial, these vectors, can it be written as a linear combination of P1, P2, and P3? So again, you set up these equations. And you set up these equations right here, and then you compare their coefficients, the constant coefficients, the coefficients of the x, and coefficient of x squared, equate them, and you will see that these questions, whether or not this is in the span of this, is equivalent to whether or not the system has a solutions. And you can see the system has a solutions, and in fact, you need 1 of this, 0 of this, and -1 of this to get this polynomial. So therefore, this is in the span. So all these are critical, and we're going to use it again, again, and again. So make sure you know what span, the concept of span is. And I always say that span is about reachability. Can you reach these particular vectors by rescaling and summing of these vectors? And sometimes we might have redundancy. So when we have redundancy, we need another concepts of figuring out what those redundancy are. So those are the concept of linear independence. So as we have known that the span of these two vectors is R2, and the span of these three vectors is also R2. But as I asked you in class, that everyone can see that, oh, 3, 2 actually is not needed because I can get 3, 2 by taking 3 of this and 2 of this. So I don't really need 3, 2. So you can see that span is just basically on reachability. Can you reach every element in R2? But it doesn't give you a concept of, hey, actually this is not needed. So we want to be able to talk about redundancy. So the concept of redundancy is that, hey, if some of it can actually be written as a linear combination of the other two, like for example right here. So for example right here, you can see 3, 2 is 3 of this and 2 of this. So you can see 3 of this plus 2 of this minus this will actually give you the 0 vectors. And this is written right here, and you can see from here we can define the concept of redundancy. We'll be like saying that, hey, we have if we have all these vectors and you always set it up, and this is 0 vectors and this is always a constant, and you try to solve the system, and I said this system always has a solution, which is all of this k has to be 0. But if you can find non-zero solutions like this, okay, then we will say, hey, there's a redundancy in this set of vectors. Some of them is actually not needed because they are a linear combination of the other. And that gives rise to the definitions of linear independence or linear dependency of a set of vectors. So again, this is actually easier. In terms of span, you actually have to do a slightly more complicated computation. But for linear independence or linear dependency, you always set up these equations. You always take these vectors. If the question asks you, hey, if we have V1 all the way to VR, this is a set of vectors. Do we have any redundancy in these vectors? How do we figure that thing out? Well, you always set up these equations and see whether or not the only solution for the system is this, or you might have non-trivial solutions. These are called the trivial solutions. You're looking for non-trivial solution. If you have non-trivial solutions, then the vectors are said to be dependent. And if you have only trivial solutions, then these vectors are said to be linearly independent. So we have seen this before. And again, one more time, these are concepts defined on any type of vector spaces. So once we are familiar with R2, R3, please remind yourself that all this concept actually works for other vector spaces, okay? So for example, we will start with polynomial of degree at most 2, and you're given these 3 vectors. Again, I say these are vectors, okay? They are polynomial, but they are vectors in this vector space. So are they linearly independent? So again, it doesn't really matter what they ask. If they ask about linear independence, always set up these equations and solve for it. So again, compare the constant terms, the coefficient for x, the coefficient for x squared. You will extract 3 equations out of this, and these are the 3 equations, and try to solve it, and you'll see that this is the only solutions. So therefore, they are independent. So again, we change vector spaces, and then I'm asking you, hey, are these 3 vectors independent or not? Set up the equation and solve for it. I didn't solve it in detail, but as you can check, you actually need one of this, and -1 of this to make the 0 vectors. This is as zero vectors. So therefore, by definitions, they are dependent. They are not independent, so therefore dependent. So all these are pretty straightforward. And then we have talk about the concept of functions when things are a little bit more tricky. And we developed a theorem which involving the determinants of matrices involving derivative, and these are called Wronskians. And this is a powerful tools. This is a tools that you can actually apply for a polynomial and to all functions to figure out whether or not if you are given n functions, which can be differentiable. And most of the time in linear algebra, we don't deal with very strange functions. So all the functions, you can assume them to be have derivative. And the question is whether or not these functions are independent or dependent without comparing coefficient, because sometimes you just can't compare coefficient if they're not polynomial. So this theorem says that, well, you compute the Wronskian. If you want to figure out this is independent or not, you compute the Wronskian. So what's the Wronskian? The Wronskian is the determinant of this matrix right here. So if you compute the Wronskian, and if you found that the Wronskian is not identically zero in the domain of the functions, then we'll say that they are linearly independent. So these are the example, EX and E2X. Can you write EX as a linear combination of E2X? Can you write EX as a multiple of E2X, for example? And the answer is no, because if you compute the Wronskian, you get non-zero, and by the definitions, okay, the proof is up there. I'm not going to talk about it now. And you get non-zero, actually non-zero for all the x values, then we will say that they are independent. These two functions are independent. That's what the Wronskians give you, okay? So the theorem says that if the Wronskian is not zero, okay, not identically zero, then these are independent, linearly independent vectors, linear independent functions, okay? So these are concept of linear independence. Okay, so we have span, we have independence, and again, span is about reachability, independence is about redundancy. So when we have a set of vectors, when it's optimal, then we will have what we call a basis for the vector space. So assuming now you have n vectors, so you have n vectors, you put them in a set. Now, if these vectors span the vector space V and they are linearly independent, then we will say these are some special vectors because they can reach every element in this vector space V, and there's no redundancy. So this is reaching, this is no redundancy. Therefore, we give them a special name. We say that this collection of vectors is known as the basis. As a basis, because as you can see later on, basis is not unique. So as a basis for this vector space. So let's start with the very obvious basis for R3, and we can see that obviously this spans every element in R3, and they are linearly independent. So this is a basis for R3, and this is in fact what we call the standard basis. So polynomial of degree at most 2, again, you can see easily these are the standard basis. Always remember what's the definition. So it span P2 and they are independent. You can actually see that pretty easily. This is a standard basis for the vector space consists of all the 2x3 matrices. So again, these are standard basis. All right. Now, one big thing about bases is that bases are not unique, okay? For a fixed vector space, let's just take R2. There are more than one basis. So we already know in R2, this is the standard basis. Okay, let me write here. So in R2, obviously, this is a standard basis, 1, 0, and 0, 1. This is a standard basis. But I claim that this is also a basis. How do I justify my claim? Well, easy. Go through the definitions. All right, first show that it spans the entire R2, and this is how you do it. Again, you fix a vector A, B, arbitrary vectors in R2, and see whether or not we can always solve for this. Solve for K1, K2, though do not solve for A and B. If you solve for A and B, I will be very upset. Okay, so solve for K1 and K2, and you can see, hey, we do have the K1 and K2 that can do this job. Therefore, it span. And are they linearly dependent or not? Well, if you already have these computations, then you don't really have to do anything else but putting this 0 and 0. And you see that this K1 will actually has to be 0 and K2 has to be 0 by definition. They're independent. So once you have established these relationships, in linear independence or dependency is very easy to see. Okay, so they are actually span the R2, and every element in R2 can be reached can be reached. I mean, it's a way of saying it, but mathematically we say is that every element in R2 can be written as a linear combination of these two vectors. So they span and they're independent. So this, again, by definition, is the basis. So you can see we have two different bases now for R2. And are they the same? Obviously, they are not. So as you can see, we can have multiple different bases. All right, so bases are not unique. All right, so for a vector space, bases are not unique. So this is another example to show that, well, instead of the standard basis, these are also a basis for P2. How do you do that? Again, check span and check independence, and you will see that. Now, so even though bases are not unique, if we fix a basis, so let's say we fix a basis and don't change them anymore. So we have a vector space V. So we have vector space V. We pick one basis. Let's say the basis is S. So this is the basis. So this is the basis, and we don't change it anymore. Now, so because basis span, so if you take a vector V, obviously it can be written as elements in the basis. And this system always, the K1, K2, and Kn always exists because these are bases, so it's span. So we always have this numbers. And this number is uniquely defined, which means that for the same vector V, if you have another way of writing it, say instead of K1, V1, you have C1, C2, and all that. So assuming that we can write it differently, you can show that actually, even though you said you can write it differently, but they are actually the same. All these coefficients, all these constants right in front of these vectors for the same vector V is always the same. And the way to show it is pretty easy. You take this equation, subtract this equation. Sorry, take this equation, subtract this equation. We have this equation. This is zero vectors. And because of the second condition of being a basis, that they are independent, linearly independent, which means that once you set up this equation and they are independent, all these terms has to be zero. That's the reason why that all the CK and all the coefficients K and the coefficients C, they are the same. So because we have what we call unique representations, once you fix a basis and a vector space, we define coordinates as these numbers. So coordinates in linear algebra always depend on a specific basis. So we have to know what that basis is. We'll talk more about that. But once you have a basis for a vector space, once you have a basis, all these numbers in front of these vectors, if you put it as a column form, so this collection of numbers is known as the coordinates for this vector. So every vectors, you can tag them. So you can tag every vectors once you have a basis, though. If you don't have a basis, you can tag them. But once you have a basis, you can always tag them by just quoting all these numbers and put it as a column vectors. So, for example, this vectors has a coordinates, and this coordinates is given by this. Now, the notations are when the bases are not very clear. So if we want to indicate what kind of basis the coordinates depends to, so this is how we write them. So again, this is the coordinates of these vectors in a vector space with respects to this basis. Okay, so from here you can already kind of see that your vector space can be any type of vector space, but the coordinate is always an element in Rn. So you can have vector space consists of polynomial, you can have vector space of matrices, but the coordinates is always column vectors, right? So it's kind of like I say in class that it's kind of like a barcode. So if you go to grocery stores, if you can find anything, right now everything is like so out, but if you can find anything like meat, vegetable, or like whatever, even though they are like canned food, they are different kind of stuff, but the barcode is a collection of numbers and letters, so it doesn't really matter what that thing is. It doesn't really matter what are the elements in the vector space. The coordinates, kind of like the barcode, is always a column vectors. So as you can see, so for example, right here we start. So please look at this example, but in order to talk about conceptually, it's easier to look at something that's not Rn. So for example, let's just look at example 7. We already seen all this example. This is a review, so I have the rights to not talk about everything. Otherwise, what's the point? So let's look at the example 7. So we have a polynomial degree at most 2. So this is a vector space we're talking about. And we already know that this is the standard basis, and we already check actually this is another basis. So you can have two different bases. So if you pick a element in P2, so this is a polynomial of degree m-2. So if you want to write the coordinate with respect to this basis, you will have to write this polynomial as something multiply 1, something multiply x, and something multiply x squared, and try to figure out what are all these numbers. But this is trivial because you already have your px written like that. So it's trivial to see that all this number here has to be 1, 2, and -1. So put it as a column vectors. You will see this is an element in R3, and this is what we say. The coordinates of px with respects to basis b1. Okay, so as you can see very clearly, you have a polynomial, but the coordinates of a polynomial is actually an element in R3. So that's the coordinate of a polynomial with respects to this basis. Coordinates will change if your basis change. So remember, that's the reason why we have to use this notation to specify that that's a coordinate for that polynomial with respects to B1. If you change the basis, let's say you are doing it with B2, so the question now is the same polynomial. What kind of coordinates will it have if now you change the basis to B2? Well, look at the definitions. The definition says that, hey, put this polynomial here and write it as a linear combination of these vectors in this basis. 1 plus x is this, x plus x squared is this, 1 plus x squared is this. So you write, okay, the vectors in this basis and try to figure out what are those numbers, what are these numbers, so that you can get to this. And as you can see, this is not a standard basis anymore, so it's not so straightforward to see what are the K1, K2, and K3. So you actually have to compute them. How do you compute them? Set up the equation and solve for it. We don't want to do that anymore because you should be able to do that. Set up the equation and solve for K1, K2, and K3 by comparing coefficients, and you will see that this will do the job. This will do the job. So K1 will be this number, K2 will be this number, and K3 will be this number. So by definitions of coordinates, these are the coordinates now, 2, 0, and -1. Again, an element in R3, and this is the coordinates for the same polynomial, but this time you write as coordinate with respects to a different basis. That's basis B2. So it's not difficult at all if you know the definitions. All right, so the definitions for coordinates is, first of all, we have to have a basis. So once you decided to use this basis, you just have to find those numbers. If you can find those numbers, put it as a column. How difficult can that be? That will be the coordinate. Okay, so just remember, computationally, it is not difficult. You are never going to ask how to do integration by part, trick substitution, none of that. It's just always solve system of equations. But what kind of equations, system of equation you need to solve? Well, you have to understand the definitions. Simple as that. Okay, so we have seen all that actually. And we'll come back to the concept of coordinates in a minute. And now we are reviewing the concept of dimensions. So dimensions is pretty straightforward. Whereas we have a theorem that says that all the bases for a finite dimensional vector space have the same number of vectors, and we define that number of vectors in the basis as dimensions. So dimension is a pretty straightforward concept. You can't find them unless you have a basis, so you have to find the basis first. So computationally, conceptually it's easy, but computationally, every time you're given a vector space, you always have to try to find a basis first, okay? But for some vector spaces that we are very familiar with, let's say R3, we already know the standard basis, what are the standard bases, and you can count the number of vectors in the standard basis, and you count 3. So that will be defined as a dimension of that vector space. So remember that, so I don't think I need to write this down, but let's write it down. So this is one of the bases in R3. One of the bases. It doesn't really matter which basis you're taking, because the theorem says that even though the bases are different for a vector space, but the number of vectors in the basis is always the same. So count them. So 1, 2, and 3. So there are 3 vectors in this basis, the standard basis, and the dimension is defined as the number of vectors in that basis. You might ask that what if I have another basis? well, in R3, but they have 4 vectors in it. This is impossible. How do you know it's impossible? Because we have a theorem that says it's impossible. How to prove this theorem? Well, in the book is we can talk about it, or you can just read about it. But if you don't care, you just take this theorem for granted, and you'll be like, oh, that's not possible because there's someone who already proved that. If your vector space is fixed, you have a basis, count the number of vectors in that basis, and you find another basis, count the number of vectors in that different basis, the number is going to be always the same. And that numbers is called the dimensions. So again, R3, what's the dimension? 3. Polynomial degree at most 2. What's the dimensions? Find a basis, the easiest basis is standard basis, and start to count how many vectors in it. 1, 2, and 3. Therefore, you have 3. Okay. How about matrices of size 2 by 2? Well, find the easiest basis and count the number of vectors in the basis, and it is 4. And in general, you can do all this. It's pretty straightforward. The dimension of Rn is n, dimensions of Pn is n plus 1, dimensions of the vector space of size m by n is m times n. This is a little bit tricky, but you should be able to do that. Okay, so let's look at the computations. The computation is pretty easy. In order to, I mean, it's not pretty easy. I mean, once you see it, it will be easy. But if you're new, then this could be a little bit tricky. So this is the example that illustrates on how you solve questions such as, given a vector space, what's the dimensions? So given this vector space, what's the dimensions? Again, seems easy. Given this vector space, what's the dimensions? Well, okay, so in order to count dimension, you have to find a basis. So that's the most difficult part. If you can find a basis, you can ask anyone. Babies who's only a few months old can count how many vectors in the vector space in the basis. So that's not a problem. Counting the number of vectors in a basis is not a problem. Finding the basis is a problem. Okay, so first you will have to understand what this vector space means. So we talked about in class already, and I don't want to talk more about it. So hopefully you were in class. Otherwise, this is the vector space that consists of all the polynomial that satisfy these two conditions. So they must, if you substitute P1 into it and P2 into it, it has to be 0. And actually, it turns out what kind of vectors what kind of polynomial that is in this vector space is the same as what kind of vectors, okay, what kind of polynomial in this vector space of the form a plus bx plus cx squared, where the a, b, and c has to be equal to 0. Sum it up has to be equal to 0. That's coming from these conditions. And a plus 2b plus 4c, which is coming from this condition, has to be 0. So these are not all the a, b, and c that can be anything. These are all a, b, and c in this polynomial has to satisfy this condition and these conditions. And if you solve for it, you will see that all the a, b, and c has to be written as this. Okay, once you have the REF, you will see that all the a, b, and c has to satisfy all these conditions that give you polynomial that is of this form, or multiple of this form. And I actually also mentioned this in class. This is not the only way you can solve them. Actually, if I ask you to identify what kind of polynomial that is in this space, and if you know your algebra well, okay, you can write all the elements out pretty easily. These are all the elements that must be in the form of x minus 1 times x minus 2 equal to 0. And once you see that, you can also see that any polynomial that looks like this will be in here. And this 2 doesn't have to be 2. It could be anything. So anything that looks like this will be in here. This doesn't even need you to solve for the a, b, and c and r, e, f, anything. Just use your understanding from algebra. You know that, hey, polynomial, p1 has to be 0, means they must have a factor that looks like this. P2 has to be 0, they must have a factor that looks like this. So therefore, everything that's in this set will look like this. And expand them up, you will see, dude, it looks like this. All right, so now we know that everything in this vector space looks like this. Therefore, it is all spanned by this, right? Right? So the span of this vectors, this polynomial, is actually entire W, because everything in W looks like this. Everything in W looks like multiple of this, or this itself, right? So we found the span. And obviously, this span consists of only one vector, so they are obviously independent because this is a non-zero vector. So this can be a basis. So this is a basis. So this is a basis of W. Now, find any baby that is 3 months old or less and ask how many elements in this set. It will say 1, right? So that's the dimensions. So counting the number of vectors in the basis is straightforward. Coming up with the basis is harder. So, but every single question that asks you for find dimensions will require you to find a basis first. So for example, what are the bases for this vector space, which consists of all the 2 by 2 matrices that is symmetric? Symmetric means A transpose equal to A. And we already talked about this, but again, yeah, if you try to find a basis, you will see that everything that is in this set, has to be written as a linear combination of these vectors. So in fact, we can verify that the span, okay, yeah. I mean, even though we talked about this before, but the key thing is that all the symmetric matrices, the entries here and the entries here doesn't have to be the same. But the entries here and the entries here has to be the same. These two entries, if it is different, that's not symmetric anymore. So that's the key. But this number and this number here could be different. That's the reason why we need this vector and this vectors to take care of the possibility that these two numbers are different. But if it's symmetric matrix, this off-diagonal entry has to be always the same. So I don't need this. Okay, because if I have this, I have actually more than this, because I can have something that is like 0, 3, 4, 0. Okay, 3 of this and 4 of this. And if you have matrices that have entries like that, it will not be symmetric. But we are looking at symmetric matrices, so we don't need this. What we need is this. So actually, we only need 3 matrices that will be enough to get you all the symmetric matrices in this space. All right, so actually the span is this. The span is this, okay? And you can verify their independence. So this is a basis. So once you have the basis, find any baby that is 3 months old or less and say, hey, how many elements in that set? They will count 1, 2, and 3 and give you the baby language that it is 3. So the dimension is 3. That's how you do it. It's pretty straightforward. Again, find the dimensions. It's just counting the number of vectors in the basis. But the problem is, can you find a basis? Right, so we talk about some other example. You can read all this in the notes, but that's the key. All right, so now skip. All right, so now we are in section 4.6, and we are basically done enough of reviewing, and won't review all that thing anymore. We are looking at a new material, and that's change of basis. Okay, so I think it's nice to pause this video right now, because we are reviewing, and this is actually kind of like new material. So we will talk about this in the second videos, so videos on section 4.6. All right, thank you for your attention.